we covered this pretty well. So Snell's law is a pretty well known law, and I derived that in a very simple way, applied to a reflection problem for shock wave, and C naught is equal to about 4.5 cg worth to pay attention, and derive these two equation set. Anybody try to derive that equation set? It's very straight, right? Anybody derive the equation? Raise your hand. Will, you did?
Yeah, I don't stop.
Yeah, okay. And anybody else derive? You shouldn't. How many minutes you spend? About an hour. Makes sense. Okay. About an hour. Hour should be good enough. And this set is very good applications, as you will see later. So that two equations set. And here, what's the P prime? Let's start from here. Lee, what's the P prime here? Yeah, that's correct. This is shock pressure for the reflected wave. P is incident wave. PG, which is transmitted wave pressure. And what about Yono? What's the U prime? This is fluid particle velocity behind what wave? Reflection wave. This is incident wave. What about gusto? UG. Fluid particle velocity behind transmitted wave. Vice versa. Rho G, CG is young one. Characteristic impedance of air in this case, right? In this case, when I derive all this, is I used the air as UG, CG, and rho G. I could use the air, AIR, as a subscript, but rho naught, C naught is 저런? That's rho naught, C naught is characteristic impedance or impedance of water. That's what that is, right? That's water. That's what we used here. So here, this is an interface problem. So this is air, this is water. Then we use, to explain, I use the wave front. One is coming down, and another one is going up. And it was CG, rho G, and this guy water is rho naught, C naught. So now that's the this equations we developed using air-water interface. But if I replace this guy, if I replace this by rigid, then this should give the result for the rigid and water interface problem. If you change the water over there, water, as a rigid, it should give you air, rigid interface problem, right? So I say rho g, Cg, this is air impedance. I'm going to say this is infinitely greater. Well, it's really, really larger than rho naught, C naught. Rho C give you the characteristic property of the acoustic media. So I said change air into rigid. That means really make the rho G Cg larger than rho naught C naught. So I can replace that. So in this equation here, listen, look at this carefully. I'm going to divide everything, just this, top and bottom, by rho G Cg. Divide the top and bottom, rho G Cg. Okay? Then what happened? This term, cosine alpha remain as is. Cosine alpha remain as is. Over here is rho naught C naught over rho G Cg. Of course, multiplied by cosine alpha double prime, right? But rho naught C naught over rho G Cg, I can set equal to 0 because this assumption to replace air by the rigid. Okay? So down here, I'm going to say this is cosine alpha, then this is going to be 0, right? You see that, right? Say yes. Goes to right? So then the remaining part is going to be simply cosine alpha over cosine alpha, which is equal to 1. So what you have here is you have P prime top. P prime over P is equal to 1, which is equal to U prime over U. This is telling you that P prime is equal to P. Another set is, this is U prime is equal to U. Is it true for rigid surface? Don't look at me like that. Yes, of course, that's the situation, right? And goes in, comes right out. Assuming there is no energy loss, energy absorption, right, in the rigid. Everything's all coming back out. Now, so it works out good. Second equation, same thing. Divide the top and bottom by rho G Cg. Then what happened at the top? 2 rho G Cg. Then top is 2 times cosine alpha, right? Down here, rho G divided by rho G Cg. Then it's simply cosine alpha. What happened to here? Second term equal to 0. So now 2 times cosine alpha over cosine alpha, isn't it? Right? For rigid case. So I can say Pg over P is equal to 2 cosine alpha times cosine alpha, right? Another set is rho g Cg over rho naught C naught times Ug over U is equal to same thing 2. This is simply 2. Which is simply equal to the is it correct? Yeah, cosine of cosine is simply 2, isn't it? So look at this. I'm going to just zap it. This is of course 2, which means from here Pg is equal to twice of P. Replace air to the rigid Pg. This is the pressure experienced by the rigid surface, right? Is equal to twice of incident shock wave. Makes sense. So that equation is okay. But what about this part? I'm going to say this. I'm going to move this guy to that side. So it's Ug U is equal to twice rho naught C naught rho g Cg, which is equal to 0, which means Ug over U is equal to 0. Ug is equal to 0. Fluid particle in the rigid, is it 0? Yes, of course, 0. Rigid, nothing moved. So these two sets of equation you can apply for to solve quite a few problems in ship shock area. So very nice. So this is what I replace like this. This is really full. It has all the notes, comments implemented in there. That's very good. Then there is a sample, the example problem I wrote here to apply these two equation set. Okay, so this is what the result. Okay, this is what I just did for this. Okay, example problem. This example problem here is for the air-water interface problem. As I said, air-water interface problem is a big problem, which I said the other day, surface ship problem is a really problem to solve. Submarine problem for the ship shock situation, much nicer, much easier problem. Some of my students working for the beam-like long structure, which is what submarine type of the problem set. And for the surface ship is really naval ship. There are whipping problems, resonance problems, a lot of different problems. So this problem, I want you to get a good feel. So this is water. And I have this angle is a 45-degree angle, which is coming this way. This is shock wave is coming this way. See now. Of course, U is also that way, and this is U naught, which is usually set equal to 0. And the reflection wave is coming back down. This is a 45-degree angle, and of course, this wave is transmitted wave into the air. Okay, that's the thing. Then it said 1000 psi. You can say 1000 megapascal if unit bothers you. Psi is pound per square inches. I demand you learn both units. You never know. You could go out to US to study advanced degree. Who knows? So here, so alpha, this angle is alpha double prime. Have you seen this before? CG, you write out the Snell's law. Sine alpha double prime is C naught. Sine alpha. Alpha is a 45-degree. So what are you looking for? Alpha double prime. So sine alpha double prime is equal to C naught CG sine alpha 45-degree. Then you can determine alpha double prime. C naught CG 4.5. Then if you say, what's the temperature? And what's the salinity? How do I know that's exactly 4.5? It's not exactly 4.5, but when you open your heart, then 4.5 would be acceptable. For the design nature, it's good. 5,000 feet per second acoustic velocity in the water, acceptable. The person who has the analysis mind will never accept, but the person who has a design mind will accept without any problem. 형은 이리 와, 이쪽 가서 앉아, 이리 와서. 싫어? 아니, 거기 앉을래? Then it's alpha double prime happen to be 9 degree. Here, remember, this is really very simplified approach to compute all this angle. Other parameters could affect, of course, temperature effect, pressure effect, salinity effect, but that's still minor. So 9 degree. So this is a 9 degree here. And 9 degree here, about 9 degree. So if I consider the fluid particle right at that intersection, right at that moment, okay? Due to the incident shock wave, the fluid particle velocity behind the incident shock wave, which is 90 degree, will shoot in that direction. Yes or no? Yes, of course, right? And there will be reflection wave is coming down, which is called what wave? Surface reflection wave or rarefaction wave. Have you heard? Yeah. Which happen to be the tension wave, you call. What does it mean tension wave? Rarefaction wave. What does it mean rarefaction wave? Which is the wave pulling the water particle. So it's no longer compressive wave, but it's a tensile wave. And acoustic velocity and the fluid particle velocity is moving in opposite direction. I'm giving you the consequence a little bit. By solving this problem, the sign is automatically fit right. That's what you're gonna see there. But a little bit physics was happening. Okay? You will see as by solving this, U prime, you will see negative value. What does it mean? Opposite to the direction of the shock wave. So by common sense first, then you have to learn the engineering based kind of approach. So this is this way, this is U, 90 degree. I'm going to say that this is U prime. It's crowded, but it's very clear, right? And the resultant of U and U prime gonna be equal to what? UG. I'm giving you ahead of the time. I don't want to hear something like in the field. I'm sorry, I have to go get my calculator. I have to go get my note to get your answer. No. Engineers should have physics in mind ahead of the time, and you can roughly tell. Yes, that's about right. No, that's not right. So this, if you add this guy, vector summation is gonna be a little bit. It's not wiggly, it's straight up, a little bit to the right maybe. So the summation, this vector is U plus, I say it's a vector, is equal to UG vector. So it's going almost straight up. Because U and U prime are the same. It's the same. First, the common sense, physics first. U and U primes are the same. So it goes straight up. That has to be equal. At the first page I said this is U prime. If this is a U is a normal. Normal has to be same. Same magnitude and goes up. Well, let's look at roughly we know this ratio is a 3600 times difference. And UG over PG over P from the first equation of two well-known equation, then you can compute this is all non-quantity. You divide it by C, rho G, CG, you got that. Then you got the 3.97 times 10 to the minus 4, which is about 0.4 psi. This has a big value in there. This is the pressure escape into the air, because PG is a transmitted shock wave pressure into the air. In other words, you put the 1,000 pound, 1,000 kilogram and 1,000 kilogram charge there. Well, not the 1,000. The shock wave pressure is 1,000 megapascal. 1,000 megapascal. But the amount of the pressure escape into the air is how much? 0.4 psi, 0.4 megapascal. Very, very small. Almost nothing. What's the atmospheric pressure? Atmospheric pressure is 1 bar, which is equal to 14.7 psi. 14.7, we are in that pressure 24 hours a day. You don't feel it, right? Astronaut, after a month in the space, when they come back, they couldn't stand. They collapses. Why? 14.7 psi is too heavy. Heavy pressure, they can't stand straight. So they have to sit and they have to learn this pressure. So 14.7, we are under that pressure all the time. 0.4, you don't feel it. You don't feel. And 1,000 psi, how big is that? Very, very big. 1,000 pounds per square inches. That's a tremendous pressure. Only escape 0.4, remember. So, when explosion occurs in the water, whenever I conducted testing, underwater explosion testing in the pond, when I say pond, it's a big, huge pond, like put the water in the abandoned quarry, abandoned mine. It's just the depth is over 150 feet. It's huge. I do conduct the testing for 60 pound HVX1, about 15 to 20 meter away. They put the charge and everything there. I stand here. It was a very calm day. I don't feel any shock pressure. I see about 150 feet high plume goes up in front of. If it's a windy day, what happened? I get the black shower, it's all black powder mixed with the water. But calm day, I don't feel any pressure, shock pressure. But if you put your finger in the water, then what happens? It will get hurt. So you shouldn't touch the water, just away from the water in the shore. I always do that. So whenever we use the pond owned by U.S. Army, I forgot the name of that. It's Maryland. I forgot the name of the site. And they said everybody should evacuate the miles away because we have explosion testing. If you go away, miles away, you can't see anything. So no reason for underwater explosion. It's pretty safe. Very small. I want you to remember that. Make a note on rho naught, C naught. It's good for design purposes. 5 pound, not mass, this is pound force, okay? Pound force second per inch cube. Or you can just put the C naught, the C naught. And rho naught is mass density of the water. Then you can get your own value in metrics. Or you can convert this into metrics. Pound force second over inch cube. Okay? So now you know that. for the incident shock wave dynamic pressure, and you can determine, because we know the pressure 1000, then you have 200 inch per second. Then what do you expect U prime? About the same, right? So you expect the same 200 inch per second. Then PG over P is that you know this ratio, you know. What's the ratio? 1 over 3600, right? 1 over UG over U. So where I get, this is 0.7, where I get that? That's a PG over P. Is it true? P is 1000. PG is 0.4, 0.397. So divided by 1000, then you got that, right? You know this, we calculated. And you know that. Then you can compute the UG. We know the U, which is 2000. One midterm exam problem, not this time maybe. Maybe I haven't made up the problem yet. It's one of the midterm exam problem relate to this. So here, UG is, when you compute that, you see minus sign, minus 1000. P prime is tensile wave. So if you straight calculations, U prime, then you got minus 200. So U prime is 200, opposite direction to the reflected wave. This is same direction of incident wave. When you add these two together, you will get the resultant, but resultant is gonna be same as UG. So UG is up there here, 285. You compute it there. Summarizing, it's all there. There. So give some pictures in there. Surface effect. Okay, it's very clear, right? Air-water interface problem, rigid water interface problem. Two sets of problem we deal with. That's about all for the ship shock problem. Ship is in neutral buoyancy. Submarine is underneath. Of course, it's in neutral buoyancy situations. That's what you handle that. Next one is a part of course, the 3.1 surface effect. Surface. When you hear about the surface effect, you have to think immediately about the cavitation. What's the cavitation? First, the physics. Cavitation occurs near the free surface. One. Second, you will see the bubbly white water right on just below the free surface. Second. Third, water density does not become to zero. A water density goes down quite a bit. Fourth, water density goes down of course, to smaller value, which means shock wave doesn't penetrate the bulk cavitation. However, not cut off the shock wave 100% because it has raw value, mass density. Such a nature, I want you to think, it happens on the free surface. On the free surface, at the time of explosion, cavitation occurs, which covers a huge area, which you call as bulk cavitation. Bulk cavitation. Bulk cavitation. All this kind, there's no text for underwater explosion except by Professor Call, published in 1949. So it's hard to capture the art. When I really start this in 1980, wasn't easy. There are two. One makes a bulk cavitation occurs in the free surface. Anybody can tell? One makes a bulk cavitation. One makes a cavitation in the free surface. Look at me. One makes a bulk, a sun. What could make the white bubbly water? When you will see the DDG 81 Shipshack Trier movie. Even if I'm not here, if you don't mind, we'll have a class like Monday, when I have exam. Wednesday, I'm going to give you all that movie. Okay? One makes a bubbly water when explosion occurs. High pressure. Wrong. Okay. 영원. Tension wave. That's it. What does it mean, tension wave? You try to pull the water. Okay? You try to pull the water. You remember I keep saying you have an image charge, which is attractive source, you know. The fluid particle behind the shock wave should work together with the wave. But the fluid particle is so attracted, he doesn't listen to mom's advice and just took off to attractive source. Move in opposite direction to the shock wave. In other words, if you try to pull the water, density goes down. Density goes down, let's say, near zero. It does not, density doesn't go down below zero. It stay up. Pressure, even if tensile, due to the tensile wave, it just to try to pull it, it usually don't go down negative 304 psi. Usually when you try to pull the water cannot sustain the tension. Water cannot pull. So density goes down, then you have a bubbly water. Make sense? Say make sense. Willie said, geez, how can
If the water particles separate, does it mean that it becomes sort of like a gas? Like vaporizes? Vaporizing.
it becomes, first step is vaporizing. Because the water particle is trying to pull each other. It's breaking off. Before breaking off, then it's kind of start vaporizing. Water is vaporizing. Okay? About water vaporize, about the pressure is about 0.3, 0.4 psi. So the one of the criteria that the cavitation occurs is P goes to 0. Mathematically, when you solve the problem, when the cavitation starts to occur, you will compute that after we return from the conference. This is like free surface. Like you can make it finite element grid. Then you can, this is a nodal point. Explosion could occur way below. You have to go each node, whether pressure right at there, at every point is 0 or negative 0. Now your turn. I hope my turn doesn't come. So if it go down to 0 or below 0, then you reset to 0. Because water cannot sustain the tension. So water cannot get the negative pressure. Even if it can sustain about 3 or 4 negative pressure, who cares? We are talking about 1000 psi. So you set to 0. So to find the cavitation, area, then what do? Cavitation area, you go through checking, find out the point where the pressure goes to 0 or below 0. Then if its charge is right there, then you can draw the outline called the upper cavitation boundary. Then you have to also calculate so-called lower cavitation boundary. Then you can declare the bulk cavitation zone. Okay? I a little bit exaggerate. It's almost flat. This range is big. When I say big, could have a 300 or 400 feet long for something like 100-pound charge, which is 50 kilogram charge, vice versa. Then I'll show you how to compute all that. Bulk cavitation, very important. When ship is sitting here, okay, then you have a multiple charge. Then, of course, bulk cavitation occurs the next moment. In the water, it's just, think this way, it's open space, suddenly show up. Then the static water pressures is all around. Then right away the cavitation zone has to close it. So open, then close it. Something close in the water, which is so-called closure pressure. Whenever something put, like a gas bubble expanded, then contracted, then down to min, then lose balance, then it collapses. Anything collapses in the water, there is a pulse. Okay? There is a pulse. It's a secondary shock. So now suddenly you have, due to the explosion, cavitation zone occurs. It cannot sustain in the water because the water pressures is all around, has to close. Anything closed, it has a closure pulse. It's not big, but cannot neglect it. And in this zone, it could be a vaporized zone or low density zone, and shock wave cannot penetrate. But strictly speaking, it penetrates, but not as good as the homogeneous water. It's a vapor water. Got it? Got it. So this is what I'm going to talk to you the next cycle. And page 8, this you don't have to really worry. This is approximation. Nowadays you don't need approximation. But when the R is really large, something like 500 feet long, when you do a big charge, then this equation is still valid. But in our learning process, you don't have to do approximations, okay? So you don't need to use that.